So in this video, we're going to introduce the concept of the source-free RLC parallel circuit. So lots of words there, but we'll explain what all of them mean here in a minute. So to get started, let's step back to chapter 8 and think about the circuits that we talked about in that chapter. And hopefully what you'll recall is that they either had a single inductor or capacitor in them. They only had one component that could store energy. And remember, the general term for a component that can store energy is a reactive component or a reactive element. And when we derived the solution to those circuits, what we found is that their responses were governed by the solution to a single first order ordinary differential equation. Now, first order just means that those differential equations, the highest derivative term that we saw in them was a first derivative. And don't worry too much about what ordinary differential equation means. That's just in contrast to a partial differential equation where the functions that satisfy the equation have more than one variable. So a lot of terms there, but basically what we saw is that if you derived either enforced Kirchhoff's current law or Kirchhoff's voltage law, you got an expression that related either the current or the voltage, namely its derivative, to itself. And what we found is that when we guessed that the solution would be an actual exponential function based upon our knowledge of how exponential functions work, namely when you differentiate them, you get a scaled version of the function back themselves, that was in fact true. So basically what the solution process boiled down to was determining what the unknown parameter was within the argument of that exponential function and determining the unknown scaling constant by enforcing initial conditions. So chapter 9 is going to work a lot in the same way. It's just going to be that these circuits will have two reactive components. They'll have both an inductor and a capacitor. So that's where in the acronym LC, the LC portion is coming. And not surprisingly, what we'll find is that when we enforce Kirchhoff's laws on these circuits, the resulting equations that govern their dynamics will be second order differential equations, meaning that the underlying equations will involve both a second derivative term and a first derivative term. Now, we're not going to go dive into detail into all the different approaches that can be used to solve second order differential equations. In fact, we're going to take the same approach that we did in chapter 8 and basically guess a candidate solution, plug it in and see that it works. We're going to extend that concept a little bit using superposition here, and we will just solve for the initial conditions. In this case, we will need to specify two initial conditions since it is a second order differential equation in order to solve for the two unknown scaling parameters. But probably not surprising if you just take a step back and think about what's going to happen, since in first order differential equations, the types of equations we dealt with had the derivative of a function being proportional to itself. And we know, of course, that those are exponential functions. We're going to get similar type equations in this chapter. Particularly, we're going to get the second derivative of a function being related to itself and the first derivative. And hopefully you all know that the functions that exhibit that type of behavior are sinusoidal functions, but we're going to take a broader approach to looking at sinusoidal functions and actually look at complex exponential terms because they can describe both sinusoidal functions along with pure exponential functions. So lots of confusion there, I'm sure, but really what we will find is that these RLC circuits, they have a ton of applications within electronics and electrical engineering, particularly in any type of frequency selective component. So things like bandpass filters, notch filters, oscillators, and so on. So especially those of you that might be pursuing an electrical or computing pathway and going on the hardware side and working in either like radar or any type of communications applications, these are going to be incredibly important and things that you will just know like the back of your hand. What you'll find is that in that case, you don't analyze them in the time domain like we're doing now. You analyze them in the frequency domain as we're doing when we close off the course. However, in addition, even if you're going the mechanical engineering route, what you'll find is that the underlying differential equations, which govern a second order circuit, are very similar to mass spring damper systems. So anything that exhibits vibration will exhibit similar solutions to what we're going to cover in this chapter. So looking at the source-free parallel RC circuit, you see it here on the right. Not surprisingly, it's just a resistor, inductor, and capacitor all connected in series. And we're going to be able to determine the complete response to this circuit by specifying the inductor current along with the voltage across the capacitor, which since all three of these are in parallel, of course, is the same voltage across all three components. Now, one of the things your text emphasizes that's just worth noting very quickly is in practice, this could be used to model either a circuit that only contained an inductor and capacitor, and you might say, well, where would the resistor come in? Well, remember, in practice, a capacitor is not purely insulative. It's not purely an open circuit. That dielectric will have a little bit of leakage to it. That leakage current will result in actual energy loss, and this resistor could be used to actually just model the loss of energy due to that leakage current. In a similar fashion, inductors, right, generally speaking, they're made by just winding a wire around some type of magnetic core. And of course, that will have an internal resistance to it as well. So this resistor could just be serving to model the energy loss in real inductors and capacitors, or of course, it could be serving to represent a true resistance value of a component. So the text talks about a way that before we actually dive into the detailed solution of this circuit, we can just try to use our physical intuition to understand how it works. So imagine some source was connected at some point and a bunch of energy was stored in this capacitor, and we just snapped our fingers. And at that point in time, we were going to let that energy of the capacitor kind of drive the other portion of the circuit, namely the inductive load and the resistive load. Well, if this was fully charged using the passive sign convention according to the polarity that we have shown, what would happen is that the top plate of this capacitor would be at a high potential relative to the lower plate. And when it started to discharge to the resistive and inductive branches, the portion that goes through the resistive branch, that's just going to be simple Ohm's law phenomenon. And what we would find is that a portion of the energy stored in that capacitor would subsequently be dissipated. And that's going to be what we're going to find that is what is associated with what is known as damping of the underlying response to the system. So that's what's taking the energy and causing it to leave via heat. However, when current branches from the capacitor through the inductor, remember that the inductor is also an energy storing element. And even though it will try to oppose changes in the underlying current because of the V equals L di dt phenomenon, remember that kind of is not allowing the current to change instantaneously, but it's also generally opposing changes in current. It will actually establish a magnetic field and store energy in the inductor. So if you think about it, it's like energy just went from being stored in the capacitor to stored in the inductor. And that cycle will repeat. The energy that's stored in the inductor will ultimately be given back to the capacitor, and a portion will branch to the resistor, taking more energy out of the system overall. But we talked about how whenever current passes through the resistor, that is damping or energy leaving the system. But really, when it's bouncing back and forth between the inductor and capacitor, a way to describe that is this phenomenon of oscillation. So basically, you're exchanging. When you think about oscillation, you think about sinusoidal type waveforms. So basically, the mechanism of storing energy is just changing over time in this circuit. And it makes more sense when you think about it for an AC drive, which we'll look at as we close the course, but that's the case regardless of what the nature of the temporal dynamics are of the underlying current in this circuit. So I think I said everything that I wanted to say on there. Make sure to read in your text and look at this underlying diagram. It kind of makes the case of what this actual process of oscillation between energy storage in the capacitor and energy storage in the inductor looks like. But what I want to take your time and focus on now is the nature of this waveform. Look at how it has an oscillatory component to it. It kind of looks like some sort of sinusoidal function, but the amplitude of that sinusoidal function is decreasing over time. And that decrease in the amplitude over time is what is actually referred to as the damping. So the oscillation is determining how quickly this process is repeating itself, but it can't repeat itself forever because some of the energy is actually leaving the system. So how would you actually quantify the solution to this circuit? Well, the way that you, of course, would do it is you would perform nodal analysis. It's only a single node, V over R. That's just an Ohm's law term. The actual expression here so remember, we don't need to go into a lot of details here just because this will get to be a very long video, but be sure to follow all of your sign conventions and whatnot. Notice that the current in this branch will be governed through Ohm's law, V over R. Notice that the current in this branch will be governed by the relationship, the IV relationship for a capacitor, which is I equals C dV dt. And here, the relationship is for the IV relationship for an inductor is actually V equals L di dt. So what they've done is they've just written this in integral form. So this is basically the current associated with the resistive path, the current associated with the inductive path, and the current associated with the capacitive path. And just be careful with the sign convention of this minus is just fundamentally related to the passive sign convention. Now, of course, the solution to this equation will be subjected to initial conditions on both the capacitor voltage or the general voltage and the current. But what we want to do is take a derivative of this. And what we will find is if we rearrange, we get a second order differential equation that looks like what we see here. And again, we're kind of working at an abstraction level where we're not concerned necessarily about how the equation came about at this point. You know how to do that from earlier in the course. How to solve this in detail, that will be a subject of further exploration in either a dedicated differential equations course or a course within your engineering curriculum that goes into. What we're curious about is what the various nature of the solutions, possible solutions, looks like. So the way that we're going to solve this is just guess a candidate solution. We're going to choose an exponential function like we did in chapter 8 because we know it has that nice property of yielding itself when it's differentiated. However, one of the key things that we're going to do to differentiate our approach to chapter 8 is actually pick this parameter, knowing in advance that S is allowed to be an actual complex number. And if S is a complex number, what that will allow us to do is to not only model exponential decay dynamics like we saw in chapter 8, but to also model oscillatory dynamics, or things that oscillate. And the reason for that is because of the property of complex numbers being related to sinusoids, which is defined by Euler's theorem. And I thought I had a slide in that. It's actually coming in the next slide. We'll go into a little more detail. So if you take and just substitute in, and I think it's a good exercise for everyone to do, take this function of time, a e to the st, and plug it into this equation. When you differentiate it twice, right, you're going to get an s squared term. When you differentiate it once, you're going to get an s term, and here you won't get anything at all. What you will find is when you're differentiating, you not only get those s terms, you get the original function back, a e to the st. So each of these terms is going to have a common a to the e to the st term. That can be factored out. And what you will find as, again, that's why I give you the reading assignments, that way you're looking in detail in the book. You're going to have the product of the original solution, a e to the st, times some actual polynomial that involves s. And if that product is 0, what that tells you is that either the a to the st term is 0 or the polynomial is 0. Well, clearly the e to the st term, from a mathematical point of view, it can be 0. But from a practical point of view, that's a trivial solution. It's not one that we want to consider. So we're going to focus our attention on analyzing the scenarios in which that resulting polynomial is 0. And this is a polynomial that you're going to be seeing throughout the remainder of your engineering curriculum. It is called the characteristic equation. And what's really cool is this shows up here. We're solving in the time domain. But when you move to the Laplace domain, or in general the phasor or frequency domain for steady state analysis, you get the same equation. So remember that a quadratic equation like this, if we were to solve for s by the fundamental theorem of algebra, it generally has two solutions. And those two solutions in general are complex. There are scenarios in which they turn out to be real, either real repeated or real unique numbers, but in general, they also could be complex. So what we're going to do here is, rather than just assume that the solution is a single exponential function, by linearity, we're going to allow it, and by superposition, remember that those two terms are interrelated, we're going to kind of assume that it can be written as the sum of two exponential terms. And the reason that we're going to do that is related to the actual Euler's theorem that I think I was calling it Euler's. Hopefully I was pronouncing right, but it's Euler's theorem. So anyways, that is related to allow us to easily convert complex conjugate solutions, which do occur to that characteristic equation, into terms involving cosines and sines to model that oscillatory type behavior that we see earlier. So this all sounds really complex, but just stay with me because it's not really that much. Basically, someone has done all the work for you from a derivation point of view, and all we need to do is actually apply this stuff. So if you basically translate and apply the quadratic formula to that characteristic equation, right, your A is C, your B is 1 over R, and your C is 1 over L. So remember, that's like the A, B, and C in the quadratic formula, not C like a capacitor value. Go through and look at the solutions in the quadratic formula, and you get this form. Remember that this is two numbers, plus or minus, because in general there are two solutions. And you can see the conditions by which you will get complex results depending upon the argument of this square root being positive or negative. So that's really hard to interpret if you think about it, looking at that expression. So what we're going to do is try to give some kind of parameterize it in a way that we get some physical intuition. So first and foremost, what should the units of these corresponding quantities be? Well, look at the way that this solution is written in general. These parameters S1 and S2 are multiplied by t. So naturally, they have to have units of 1 over a second. And what is a unit of 1 over a second? That is a hertz. It is a frequency. So what we're going to call those two numbers that we have above, the S1 and S2 terms, are complex frequencies. So they're complex. They're not just normal frequencies, because they're not just describing oscillation, they're also describing damping. But let's go a little bit further, and let's actually try to break that up into a parameter that describes how quickly the response is going to 0. We'll call that alpha, and we'll call it the damping coefficient. And I'll give you the formula on the next slide, but you can probably spot that it's basically just going to be what is outside of the square root here, because that's what's going to determine the basic real part of that exponential. In addition, let's define a parameter that describes how quickly the oscillation is occurring. frequency in the traditional sense, and we'll call that the resonant frequency, denoted by omega sub 0. You also hear it called omega naught sometimes. So formulas governing the overall system, the omega naught, which is determining how quickly it actually repeats itself, is going to be solely a function of the reactive components of this circuit, namely 1 over the square root of LC. The damping coefficient, not surprisingly, is going to involve the resistive term along with the capacitive term, and it's just going to be 1 over 2 RC. So you can go back and see where these are coming from. This is the damping coefficient because if you plug this into the argument of E and then use your properties of exponents, what you will find is that that always is an E to the minus something T term. So it's always going to be decay. That is your resonant frequency, and we won't go into why that is because we want this video to be short. And you can rewrite the actual complex frequencies that we had here. So this is S1 and S2. We can rewrite them here. They're expressed in terms of RNC, which isn't surprising because we just applied the quadratic formula to here. But if we make these definitions of omega naught and alpha as a function of LNC, we can express the complex frequencies as minus alpha plus square root of alpha squared minus omega squared, and this is just going to be the potential conjugate of that. So a lot of stuff to go there, but what you find is that these complex frequencies and these values of alpha and omega naught give us a way to not only interpret the physical intuition of the circuit, but also they give the complete solution to the circuit as long as we know the initial conditions. So one thing that you kind of need to remember is that there are 3 different scenarios that could occur with respect to the relationship between alpha and omega naught. So your actual damping factor and your resonant frequency. If the damping factor is bigger than the resonant frequency, we will call that an overdamped solution. But what it means from actual solutions to the characteristic equation, or what we'll eventually see are called eigenvalues of this underlying system, is that they are going to be 2 real values and they're not going to be equal to one another. If the alpha and omega naught term are actually equal, you're still going to get real solutions, but they're going to be equal to one another. That's the case where you have a repeated root in a quadratic. And finally, if alpha is less than omega naught, that is going to be an underdamped solution or an underdamped system. And what that's going to mean is that the complex frequencies S1 and S2 are going to be complex conjugates of one another. So really, this is just going back to wherever you saw quadratic equations originally in a college algebra type course and reflecting upon the fact that when you solve a quadratic, you got in general 2 solutions. They're either real unique, real repeated, or complex conjugates. So let's look at an actual example here of putting this into practice. If we have a parallel RL circuit, we know that the inductance value is 10 millihenries and the capacitance value is 100 microfarads. So right away, hopefully you see parallel RLC circuit. I'm analyzing it in the time domain. I know that it's going to have, generally speaking, some type of second order dynamics. And the nature of the dynamics are either going to be pure exponential decay or they're going to be oscillation with decay. Really, it's just a matter of determining which scenario we're dealing with. And that's going to be a function of the parameter values. Remember that the inductance and capacitance, you don't have to remember the formula necessarily for this class, even though if you're going down the electrical and computer engineering route, you won't have a choice. It will get engraved in your head. Determine the actual resonant frequency. So right away, you know in your head, if I had the inductance value and I had the capacitance value, I can determine the resonant frequency. But what I don't know, just given those 2 values, is the actual damping coefficient. I don't know how quickly this is going to 0. So what they ask us is to determine the resistor value that would lead to an overdamped and underdamped response. So let's think about the way where we're going to do this. Remember that the relationship between overdamping and underdamping is all related to the relationship between omega naught and alpha. Alpha depends on R, but omega naught does not. So I will be able to calculate omega naught given L and C. And then I know that if I want it to be overdamped, I just need alpha to be greater than omega naught. Alpha expression involves R and C. So I will eventually be able to get this down to an inequality that only has one unknown and solve for it. Now let me show you how to do that just to save time. I wrote this up in advance and looks like it's a little bit hard to read. Let me get some lighting on it. Zoom in a little bit. So we're given these 2 values of the inductor and capacitor, and we want to find R for overdamping and underdamping conditions. So let's just start arbitrarily with the overdamping solution. We know when an overdamping that the damping coefficient exceeds the resonant frequency. We know that the resonant frequency is given as a function of L and C, 1 over square root of LC. Get really comfortable with doing actual scientific notation manipulations quickly. I did these all in your head. You'll find it a lot of times for exam problems and homework problems. There's things that can be done really quickly in your head. Be also sure to know that you have the metric prefixes like the back of your hand. So if it's 10 millihenries, 10 times 10 to the negative third. If it's 100 microfarads, 100 times 10 to the negative 6. just put all these together, 1 factor of 10, 2 factors of 10, that's 3 positive factors of 10. That will effectively cancel out the 3 negative factors of 10, leaving you with only 10 to the negative 6 under the square root sign. Remember, when you have an exponential term under the square root sign, just cut the exponent in half. So that's 1 over 10 to the negative third, which is 10 to the positive third. That is in units like all of the complex frequencies in actual hertz, but particularly 1,000 hertz would be 1 kilohertz. In order to be overdamped, the damping coefficient alpha has to exceed this value. So I just need to pick alpha greater than 10 to the third. I know that alpha is a function of both the resistance and capacitive value. So I can get this singly as a function of the resistor value. Just plug in your C and simplify, and then set this to be greater than the actual resonant frequency value. Be careful with your algebraic manipulations, and what you should find is that you need the resistor value to be less than 5 ohms in order to be overdamped. Well, think about the solutions for the underdamped case. That's going to be the same inequality, it's just the direction of this comparison operator is going to be swapped. So you can kind of argue with yourself there, or just plug it in if you want to see it, but all that's going to happen is that the resistor value doesn't need to be less than 5 ohms, as was the overdamped case. It needs to be greater than 5 ohms in this case. So I know that was a really long actual video, and I hope that it provided some insight to you with how this works. 20 minutes is way too long, but the good news is a lot of what we're going to do in the next few modules build upon this actual content.